Let's do a little merging magic. So the big picture here is that selection sort is slow and merging is fast. So what we're going to do is take our array of, say, size 64 and split it into two arrays of size 32. The idea here being that since selection sort is slow, it will derive a tremendous improvement by giving it a smaller array. So rather than taking 2048 arbitrary units of time, each of these selection sorts will take only 512. And the astute observer will note that the total amount here of work at the selection sort level is 1024. Now, of course, selection sorting two smaller arrays does not give us the answer because we have two arrays. We need to somehow combine them, but we have merging to do that for us. So in the end, the total amount of work we end up doing is around 1024 arbitrary units of work to do the sorting, and 64 arbitrary units of work, roughly speaking, to merge everything into one big array. And so overall, our total runtime is a little more than half of what a single selection sort all at once is going to take. Now, this arbitrary unit business, it's a little hokey, a little hand-wavy, but it's pretty close to the truth. And if you want, what you can do is run an experiment and prove to yourself that indeed it really works. Another way, if you don't like the numbers, is, well, we could say we had an n squared algorithm, but now we have an n plus 2 times n over 2 squared algorithm. And this expression for any value of n is going to be smaller than this one for integers. Now, I personally find it difficult to visually look at this and say, yeah, that's better than that. Hence the fact that I'm using these numbers throughout this discussion. Now, it's a little unconventional because I think the math, again, it's a little hand-wavy, but I find it really intuitive and it kind of hits me in the gut. It's an emotional reaction. I see 1088 and I want to hoot and holler and yell to the heavens about how much better this is. And I find it hard personally to get excited about n plus 2 times n over 2 squared. Okay. Now, we shouldn't be satisfied with what we've achieved because we can do better, as indicated on this slide. Rather than breaking things down into two arrays, we could break it into, say, 4, each of size 16. 16 squared is 128, so the total amount of work needed to selection sort these 4 arrays is actually only 512. So it's 4 times 16 squared. Now, 512 is a lot better than 2048, but we have some overhead because we have to somehow take these 4 arrays and combine them into a single array. Now, the most natural way to do that is to do a 2-layer merge, where we take our 2 arrays on the left of size 16, merge them into an array of size 32. We repeat that for the other side. We get another array of size 32, and we merge all of those, or both of those arrays, into one giant array at the end. You could, I guess, make a different version of merge that takes 4 arrays, and that might be an interesting question that you can consider on your own, but I'm going to do it this way because it will lend itself to the analysis I want to do. So what we end up with here, with this merge magic, is with 2 layers, we only do 640 arbitrary units of work, which is almost 4 times as fast as our original algorithm. But we still shouldn't be satisfied. We could actually break things down further and make 8 arrays of size 8, or 16 arrays of size 4, or even go crazier and go all the way down until we have only arrays of size 1. So here's a question. If you have an array of size 1 and you selection sort it, is that fast? Yeah, it's pretty fast. Do you actually need to selection sort? No. So what you can do actually is if you merge all the way down, you end up basically getting rid of any actual sorting, right? Any special sorting algorithm, and the merging does everything. And so we end up with an algorithm that perhaps you've seen before called merge sort, which I find one of the most interesting and amazing and beautiful algorithms because it just evolves naturally, right? I mean, this is very intuitive, the notion of, I just, cut it into smaller pieces. But what's fun is if you cut it down into the pieces that are size 1, the whole process still works. You can divide and conquer all the way down. So what merge sort ends up looking like in code is roughly something like this. If our array is of size 1, don't do anything. However, if we have stuff to do, we'll split it into 2 halves. We'll merge sort the left and merge sort the right. And then finally, we'll merge the results. And here, when I say merge sort, I mean doing this whole process. So it's a recursive sorting algorithm, and a very fast one at that. So what we end up with is rather than taking 2048 arbitrary units of time, merging only will take around 384. And this is the argument. So at the top level, we do 64 units of work to merge our size 32 arrays. The next layer, we have 2 merges where we're taking size 16 arrays and turning them into size 32 arrays. And so the total amount of work is 64. Well, the next layer down, actually also 64 units of work because it's 4 merges, each taking 16 units of work, and so forth. And so we go all the way down so that we have a 64 layer, a 32 layer, a 16 layer, an 8 layer, a 4 layer, and a 2 layer, and that's it. And so in that case, k is going to be, so if we say k is the number of layers, k is going to be 6. The overall amount of work is 64. And so we say that it's 384 total units of work. So keeping in mind that what we have here is log base 2 of 64. Cut a thing in half over and over, it's going to take log base 2 to get down to the atomic level or a single item. So that's merge sort. So what is the runtime of this recursive algorithm? In other words, if we plug into these question marks, what do we get? And so one thing I think, this is going to be the question you're going to answer, that I think is really interesting, to me at least, when I first learned this, is we have an algorithm that is n squared. By adding a layer of merging, we get something that's still n squared. This expression here, still n squared. We add another layer, still n squared. And the question is, if you repeat that over and over, do you end up with an algorithm that is still n squared, just a faster n squared? Or is it actually a totally different order of growth? Think about that, ponder that for a few minutes, and then I will tell you my answer. Okay, so it turns out that it is actually a different order of growth. And in fact, if we parallel the argument that we had on this slide, except now with symbols instead of the number 64, we get our answer. So every layer, this is the most important part of this argument, every single layer takes the same amount of work, namely n. This top layer takes n work. This one takes 2 times n over 2 work, which is n. This one takes 4 times n over 4 work, and so forth. So that all the way down, every single layer, we're always doing n levels or n units of work at each level, and the total number of layers is going to be, well, in this case, k, which is going to be log base 2 of n. And so the total runtime is nk, where k is itself a function of n, so we can't just treat it like a constant. It is a function of n. And so the overall runtime is n log n. So by repeatedly dividing and conquering all the way down, we get an algorithm that is n squared to n log n. That's what the transition we've made. Now there's a couple caveats here, or one main caveat, which is you can't cut every array in half, right? If you have an array of size 7, you don't get 2 arrays of size 3.5. In the textbook exercises, you can convince yourself that this really works even for not powers of 2, but it turns out it's just a tedious set of tweaks, okay? I think this argument's good enough. I think it's a wonderful argument. It's intuitive and clear to me. And if it's not yet for you, explain it to somebody else until it becomes clear to you. And just repeat this process all the way until everyone has had this explained to them in the whole world. Okay, now there is an alternate explanation if you want a more mathy version where we have a recurrence relation. I'm not going to go through this argument, but if you want, here it is. Okay, one last thing I want to reflect on before we summarize what we've achieved in this lecture, which is that merge sort is a really, really, really good sort. Not only is it beautiful and amazing and almost as simple as it could possibly be, but it's also extremely fast, much faster than selection sort. Like, it's a completely game-changing level of faster. If we go from n squared to n log n in our table from before, we take an algorithm that would take 12 days on an array of size 1 million, on a computer doing 1 million operations per second, to taking 20 seconds. And what's actually interesting is that n log n and n, while they are different families, they're not that different. N log n, well, if you think about 1 million, log base 2 of 1 million is only 20. So the runtime is only going to be about 20 times slower. And if you go up to size 1 billion, the difference between n and n log n isn't going to be much different, but n squared is going to be far worse. So n and n log n are pretty close, and n squared is far worse. And so we've achieved something actually incredibly important. If we lived in a world where sorts were all n squared somehow, like nobody had invented any n log n sorts, things would be slow. I mean, a lot of technology we take for granted probably wouldn't even work because sorting is at the heart of so much that we do. And so that is, I mean, a tremendous achievement that I think can be hard to see, but something that is incredibly important that we have done so far. Okay, good job. We did it. Merge sort. Make sure you know it well. That same pattern of analysis is going to come up over and over in this class. So make sure this argument made sense.